of those sources are the planet-forming disks. That's where we go to members of the public and ask for their help figuring out which of those needles in the haystack is a real planet-forming disk. No experience necessary. There's a short online tutorial. In about 5 minutes, you're looking at data, you're helping NASA, and you're potentially making discoveries.
NASA has many satellites orbiting the Earth that look at clouds from above, but we need your help to make matching observations from below. By getting the perspective from both sides, we can have a more complete picture of what's happening with clouds in the atmosphere. Satellites see clouds differently than human observers, and NASA scientists could never be in all the places they would like to be to collect data from the ground, which is why we need your help making observations.
So we've been traveling around the world using drones and this technique to map corals in 3D. And the biggest challenge we have with all of this data is how to classify it. How do we get the basic number of how many corals there are, how they're doing as a function of changing ocean temperatures? And that's where NemoNet comes in. So we built a video game that ties into our supercomputer, and you can download it and play it on your iPhone or iPad device. And what you're doing in that game is looking at our data sets that we are getting from around the world with these drones and helping learn about corals at the same time as coloring them and feeding data into our supercomputer.
On Planet Hunters TESS, we use data obtained by NASA's Transiting Exoplanet Survey Satellite, or TESS. So TESS is a space-based satellite that monitors the brightness of thousands of stars, and we need your help to find the planets within these data. In particular, we want to find the planets that the machine and computer algorithms tend to miss.
So auroras affect our technologies on Earth and in the sky in satellites, and they move really quickly, and it's important to get an understanding of what they're doing, and citizen scientists can really help with that.
What kind of discoveries have citizen scientists made with this project?
So one big one is something called Steve, which is actually an aurora that can be seen further away from the poles than the usual aurora. It's very unusual. It kind of looks like an airplane condensation trail, but with a photograph you can pick up these amazing colors as well. By studying it further with satellite data and other data from the ground, we've discovered it's really like a flow-driven aurora. It's an east to west flow that is lighting up the sky and doing some amazing kind of new, unusual auroral activity that's still being studied now.
We astronomers thought that disks stopped forming planets after about 5 million years, but then the citizen scientists at Disk Detective started finding objects that were able to form planets about 9 or 10 times the age of that, so into the 40 and 50 million year old age range. And the astronomy community is still trying to figure out what that means, so it's pretty exciting.
The second is, once you have all that data, it really doesn't mean anything unless you have humans come in and help annotate what it is we're looking at. To put it bluntly, they're changing the world. I mean, we have mapped, as of 2020, around 6% of the ocean floor.
Project in 2006, I think we had like 5 teams participating. Now we've got over 3,000 teams from 80 countries around the world that participate. Citizen scientists are able to look at these images and see deeper into the images than the automated detection utilities. Those are important observations because they're finding things that are missed in the original data.
Hello, my name is McDonald Chirara, and I've been part of the Globe Observer program, which is part of NASA's Citizen Science project. I've been involved in this project for the past 6 months. I decided to participate in this project so that I get the opportunity to do something cool and interesting in my free time.
Please join us because it's a very exciting thing to be involved with, to be able to report and share what I see. I'm not a scientist, I don't have a great camera, I'm not a professional, but I can be involved in something that's really important. And
Hey everybody, greetings from the Arctic. Team Hearts in the Ice, saying hi.
Hi.
We want everybody at the CitSciCon to be super citizen science heroes.
It's so much fun. Join in.
All right, so now I know we have some attendees who are here a little early. Welcome, everybody. We're going to do a quick sound check with our panel and our moderator today. So we'll start off with Phil Plait, the Bad Astronomer. Phil, if you want to unmute and maybe tell us something you're excited about or a cool fun fact for your sound test, that'd be great.
Hi, I'm Phil Plait, the Bad Astronomer, and I'm excited about everything. So there's no way to narrow that down.
All right. Let's have Nora Eisner do her sound check next. Nora, what's something you're excited about?
Hi. At the moment in my work, I'm very excited about a triple star system. But yeah.
Oh my gosh, tell us more.
It's compact. There's a lot of stars. We don't know what's going on. I think that's the exciting bit. We have no idea what's going on.
That is exciting. Okay, up next, Adam, if you want to do your quick sound check and tell us something you're excited about.
Hi, hopefully you can hear me. I'm Adam, and I'm super excited about a lot of discoveries we've made. We've got a bunch coming out this summer, so so much good stuff happening, and I'm excited about this conference, period. Putting together this talk was amazing, so.
Awesome. Yeah, and we'll hear more in your talk about things you're excited about, I'm very sure. And then last but not least, Stephen, tell us something you're excited about for your sound check.
I am excited to hear about all the amazing science everyone else is doing to go with the amazing science our citizen scientists are doing at Disk Detective.
Awesome. Well, we're going to officially get started in about 5 minutes. And in the meantime, you'll just be seeing some slides on the loop while we wait for the official start time. I'm going to pass the mic to our moderator, Phil Plait, until we officially get started at 3:15 Eastern.
Should I sing or say something or just wait?
You can do anything you'd like. We usually just chat for a little bit while we wait for our official start time. I'm seeing someone in the chat said definitely sing. So you could definitely sing if you would like.
Yeah, no, that's not going to happen. But actually, just telling me I can do anything I like is probably extraordinarily dangerous. But I want to know, actually, Nora, this triple system, this trinary, can you tell us which one it is, or is it still kind of shouldn't be talking about it yet?
It's a test target. I don't. They have so many different names of different stars. I personally call it Fluffy. That's just a nickname I give it. I have so many systems that I look into that I like to give everything a nickname. This one, for any Harry Potter fans out there, I call it Fluffy because 3 components, 3-headed dog in Harry Potter. But yeah, it's very fun. We're currently writing it up and trying to figure out what it all means.
Do we know of any planets orbiting in a trinary system?
There are no planets in the system. I should say, sorry, even though it was found on Planet Hunters, there are no planets in the system as far as we know.
I see.
This is purely just some very interesting stars. There's a planet known around a quadruple system that was found with the Kepler Planet Hunters.
Oh, okay. I probably knew that. It's 4,000 planets and counting. It's kind of hard to keep track of everything that's going on.
Yeah, the Harry Potter nicknames can't keep up, so.
None of the names can, and it's distressing. I actually see there's a question in the Q&A already saying if we discover a new planet, what do we call it? And there are protocols for that. We typically name them after the star. So the star has either a proper name or a number or a catalog number, and then every planet gets a lowercase English letter after it. And it's getting tough to keep them straight. And and people say, why don't we give them proper names? And the answer is, we already have 4,000 confirmed planets. What are we going to call them? So we're just going to run out of names too quickly. I don't know how we're going to deal with this in the future.
And really quickly, I do have one last kind of tech sound check kind of question for everybody. So in terms of our slide deck for today, of course, Phil, when you're doing your intro, we'll be advancing the slides for you with our welcome and the polls. Then for Adam, we'll be advancing your slides, so you can just say next slide. And then our understanding is for Stephen and Nora, you'll be showing your own slides. So we'll just stop sharing when we get to your parts and let you take it away until we get to the Q&A. Does that sound good to everybody?
Are we live in front of the audience now?
We are. So we do.
That's what I thought. Okay. I didn't want to just start.
Transparent.
It's like I'm speechifying already. And it's like, if I'm just talking to 3 experts on planet hunting, that's a little silly, a little presumptuous on my part.
Yeah. Everyone's saying hello to us in the chat. We got people from Utah, Germany, all sorts of places.
Utah and Germany are very similar places.
Great. But yes, that's how we're going to be running the slides today. Any last technical questions for our panel in our 2 minutes before we formally start? I see shaked heads. All right. I think we're good. Great. We have 1 minute left till start time. And as an FYI to everybody watching, we are recording this and it is live on YouTube and Facebook. And if you want to communicate with us, of course, you can use that chat, but we're going to be really monitoring that Q&A. And we'd like to encourage the whole panel, when you're not presenting, if you want to answer questions in the Q&A, you can just type answers to participants. We really encourage that. We think it's a fun way to talk to everybody.
Questions are already racking up in the Q&A.
Great. Yeah, and people are still saying hello in the chat, which is great. Keep that going. We're going to start in 1 minute. And we're at start, so we'll hand the mic over to you, Phil.
Thank you. Hi, everybody, and welcome to CitSciCon and to this panel, which is called Planet Palooza, where you are going to find out how you can actually use real data to look for objects in space, planets, brown dwarfs, forming planets, all kinds of cool stuff. And this is a real effort using real science that gets real results. There have been a lot of amazing things that have come out of these things. Now, I actually have something I don't usually do. I have a list of stuff to talk about because there's just a lot of stuff here. We are on Zoom and Facebook and YouTube. We have, I'm not even sure how many people watching now, a lot, in fact. If you have a question and you're in Zoom, hit the Q&A button, write it in there, and we'll have somebody look at it. If you're on Facebook or YouTube, just leave a comment. There are moderators there, and they will be happy to take a look and pass that on either to me and the panelists, or they'll answer you right there. Now, if you're just tuning in, citizen science is where people who are not necessarily trained in formal science get to participate in scientific research using actual data. There are a lot of ways that this is being done. It's been done for a long time too. NASA is a big proponent of this. They make a lot of their data, actually all the data, public. So it's possible to actually go through it and do stuff, look at it, analyze it. Computers do this for the most part, but it's tough to look for things that are moving, things that are faint, things that are maybe hiding in crowded fields with lots of stars. Computers aren't that good at that, but our brains have had a long time to evolve and do pattern recognition. So we're actually really quite good at this, sometimes even better than computers. So SciStarter here is organizing all of this with the help of NASA. If you want to participate in this, SciStarter organizes it. Go to scistarter.org/NASA, and you can sign in there and be a part of this, which is really cool. I love, love, love citizen science. You've probably heard of citizen science results, even if you're not aware of it, like Boyajian star, that weird star that undergoes huge fluctuations in brightness. And we thought maybe for a little while had aliens building stuff around it. Maybe, turns out not so much. but still very exciting. We still don't know what that star is doing and why. So citizen scientists found that star, and a professional astronomer then took it from there. So that's all very cool. And that's what we're going to talk about here. So having introduced the topic, hi, I'm Phil Plait. I am actually an astronomer. I studied a lot of different things back when I was doing research with Hubble and various other observatories. But since then, I have been more interested in talking about this sort of thing, writing about it, talking about it in interviews and TV and that sort of thing, because I love astronomy a lot. And while I love doing it, I love sharing that knowledge and the passion that I have and the joy that I get from it with the public. So that's why I am here doing this. I'm very excited to be here. And let's see, that's 3 minutes. I have what? 7 more minutes? I don't even, should I read my PhD now? No, I don't think so. That's probably a terrible idea. The 3 citizen science projects, excuse me. I was going to say something, but that's slightly out of order. We have a poll that is going up on Zoom, I believe it is. And it's asking who's with us today. If you can see that poll, it just popped up on my screen. Are you all seeing it too, panelists? Yeah, I'm seeing nods. Excellent. It asks, are you a citizen scientist or aspiring citizen scientist, a student, a parent of a citizen scientist or aspiring citizen scientist, library or museum staff and or informal educator, formal educator, or something else? And if you're something else, share it in the chat. Let us know what you are. Go ahead and hit a button there. And as always, I never know what I am. I never seem to fit into any of these polls, but let's see here. We're already getting results. We've got 178 people who have already hit the button. That's pretty cool. And wow, 2/3, 66% are citizen scientists or aspiring citizen scientists. I like that. That's good to see. A lot of them, 34%, so 1/3 are students. We've got a handful of parents and library and museum staff. I love hearing from libraries and museums, my favorite places in the world. Formal educators, so people who actually are trained to teach and teach students, 10%, not bad. And other, 7%. I think I'm other there. I don't think they have a button there from panel moderator, so we'll call that 7.5%. So we have another poll up now. Have you participated in citizen science? And the 4 options are yes for more than 1 year, yes for less than 1 year. If you've done it exactly 1 year, sorry, you can't fill this one out. No, I have not participated in citizen science before, or I'm not sure yet. So go ahead and pick one of those. And I'm going to say yes for more than a year because I have, except I can't click on it. It's not for me. Hosts and panelists cannot vote. Fine. All right, let's see what we got here from everybody else. A little more evenly split now. We have 39% yes for more than a year, 25% for less than a year. That's good. That means we have a bunch of seasoned pros in here, as well as people who want to know more about this or are learning how to do this. And 35% who have not participated before. That's great because that means 1/3 of y'all are going to find out how cool this is to do. And 1% not sure. Well, that's like 1 person, maybe 2. So let's see if we can get them off the fence and into our corner. So there we go. There are the Zoom polls. So now I shall introduce our panelists very briefly. Just going to let you know who they are and what they're working for, and I'll throw it to them and let them go into a little bit more detail because nobody knows what they're doing like the person who's doing it. So we have 3 citizen science projects here using NASA data where you can look at this data and try to find objects in it. And before we even start, I'm going to say it sounds a little weird maybe if you've never done this kind of thing before. It is hugely fun. It is so cool to know you're using real data, but also it's just a lot of fun to dig in and start looking for stuff. So we have Adam Schneider with Backyard Worlds Planet 9. I'm very excited to hear about this because I'm a big Planet 9 aficionado. I'm very interested in this and very interested in what's going on in the solar system out past Neptune. Steven Silverberg from Disk Detectives, looking at planets that are forming around other stars. Also something I studied for a while, also very interested in that. And Nora Eisner with Planet Hunters TESS. Again, something I'm very interested in, using these amazing NASA missions, which are dedicated to finding planets around other stars. So I'm going to throw it to the first panelist here, and that's going to be Adam Schneider, who's going to talk to you about backyard worlds and looking for Planet 9.
Awesome. Thank you so much, Phil. What a great intro, and thanks for being here. Yes, Backyard Worlds Planet 9. There we are, first slide. So hello, everyone. I'm Adam Schneider. I'm one of the co-founders of the Backyard Worlds Planet 9 project, and I'm super excited to be here to talk to you about our project and ways you could join in and help us discover new things in our galactic neighborhood. So there are two big questions we're really trying to answer. The first one, is there a large planet at the fringes of our solar system awaiting discovery? So a few years ago, in case you didn't know, some astronomers predicted that there might be a large planet at the outskirts of our solar system that's affecting the way other things out there in the solar system are moving around. Called it Planet 9. It hasn't quite been discovered yet, but the really interesting thing is, and the reason that we're doing this project, is we may have taken its picture already, which is fascinating. The problem is the sky is really, really big. And so we need a lot of eyes to look at a lot of images at the right time to see if we can try and find it. And so that's one of the main things we are doing in our project. The other question we want to talk about is what else lurks just beyond the edges of our solar system in our galactic backyard, so to speak. So the else in this question are objects that we lovingly refer to as brown dwarfs. They look something like the image you're seeing on the right side of your screen in this artist's impression. They are fascinating objects that lie just beyond our solar system. And what's really interesting is they've historically been very, very hard to find. And it turns out some of our very nearest neighbors in our galactic backyard are brown dwarfs. And since they're so hard to see, we can discover more and more of them around us all the time. So brown dwarfs, you can think of them a little like Jupiter, but a bit more massive, a bit warmer, and out there floating on their own. So they're not orbiting a star in most cases. And so they look kind of like what you see in this image. Again, this is an artist's impression. One great side note about this artist's impression is this was actually created by one of our our volunteers from the project and used in one of our NASA press releases for one of our discoveries. So Billy Pendrell, thank you so much for the artwork and a good way to describe brown dwarfs. If we could please go to the next slide. Okay, so the way we actually try and find these objects is fairly simple. So NASA has this amazing telescope called the Wide Field Infrared Survey Explorer, or WISE for short. And what WISE does is it surveys the entire sky at infrared wavelengths, and it's been doing this for several years. And so Planet 9, if it exists, is in our solar system, so should move with some orbital motion. And nearby objects just outside of our solar system should move relatively quickly compared to everything else that's much, much further away, just because they are so close. And so what we do is we look for that movement. And so the way we do this is we take WISE images separated by a few years and we subtract them from each other. The idea being that non-moving things further away will just subtract out and moving stuff will pop out and be highlighted. So when you log on to Backyard Worlds and go visit the site, you will be presented with an image very similar to this. And you just look for moving objects. There's a very simple marking tool that you can mark your moving object if you see one. And then if you want to be done, you're done. You have contributed to science if you mark a moving object. So we also have in place several tools and tutorials if you would like to dig a little deeper, which a lot of our volunteers like to do. So if you think you have found something, you can go look and see possibly if you've made a new discovery, or see if it's something that's known already. And you can see like, oh my gosh, I discovered this thing that somebody else has already found that's really interesting. If you do think you have something new, we have something that we call the Think You've Got One form. And so you can put your object right in that form, send it to us, and it goes right to the science team. So that's been a really great way for volunteers to send us potential new discoveries right away. And it's been working really, really well. Next slide, please. So we would not be very far if we didn't have an amazing group of volunteers with us. These are just a small sampling of some of our great collaborators that we work with. As you can see, they come from all over the world, many different backgrounds, all ages. And just to point out, recently we've had what I think is probably our youngest collaborator. He was Jake Roberts down there at the bottom left. His grandfather is a volunteer on the project, has been with us for several years. He's actually did the artwork from page 1 or from slide 1. And he was hanging out with Grandpa and Grandpa was showing him the project and he's, going through a few and was like, hey, Grandpa, what's this? And turns out it's a discovery. We're trying to follow it up. So when I say we try to make it accessible to everybody, we really tried to make it accessible for everybody. And we've really gotten discoveries from all over the place. So that's really exciting. When it comes to results, if you can look at it as good news or bad news, we haven't found Planet 9 yet. If we did, we'd be very excited. We'd tell you. We haven't found it yet. So that could mean maybe it's not there, maybe it's beyond our reach of our images, or maybe we just, like I said, haven't had the right person with the right image at the right time find that object. So if it's out there, it could potentially still be in our images, and we'd love for you to come and try and help us find it. When it comes to brown dwarfs in the solar neighborhood, we exceeded expectations is severely understated. We have found so many new brown dwarfs that we are having a hard time keeping up. We are doing so well in this area, it's amazing. We can't publish fast enough. So we have over 3,000 new brown dwarf discoveries, and that's almost as many as have been found in all of history before this, right? So we are on that level. And when we talk about mapping our solar neighborhood, when we're looking at our backyard, like what are the nearest objects to us? In 20 parsecs, which is something like 65 light years. So this is a fairly local region of our galaxy. Of the 500 or so brown dwarfs that have been found, 20% came from our project. So we are making a really significant impact on the map of our solar neighborhood. And our impact goes well beyond that. Just mapping the galaxy, we have so many other high impact discoveries, from extreme subdwarfs to co-moving companions, planetary mass companions, free floating planetary mass objects, like you name it, they're popping up in our searches. And we have so much coming and so much that we've already done that we're super excited about. And some of our objects have even ended up on James Webb Space Telescope observing list. So some objects discovered through our program are going to be observed with the biggest, greatest telescope we've ever made as humans. So that's really exciting. Hubble as well, observing some of our objects. So we're super excited about that. Okay, next slide, please. All right, so if any of that sounds interesting to you, please come join us. Go to scistutter.org/NASA and find Backyard World's Planet 9. There's a short tutorial, and you could be the next one to make a discovery in our backyard. We're showing some of our nearest discoveries over here on the right, just bopping around as they move around the stars over there. So the next one could be yours, so please come join us. That's it.
Fantastic. I've used this actually, and I've quite enjoyed it. And I want to clear up something you said, Adam, actually, if you can unmute yourself just for a sec. Backyard Worlds has found 3,000 brown dwarfs?
So yes, I would call them candidates for now, but
okay.
But knowing, so we're trying to follow them all up spectroscopically to make sure, we know their spectral types and things like that. But we have color information and they're moving. There's not much else they can be in most cases, although some things surprise us all the time. So I wouldn't say 3,000 confirmed brown dwarfs, but we probably have 3,000 brown dwarfs at that.
3,000 possible brown dwarfs. That number is jaw-dropping to me, because when I was a young astronomer working on Hubble, we knew of like 10.
Yes.
And we observed one of the first ones ever discovered, and we got the first data on it in that particular way. And now it's just all the time. So It's amazing how quickly these fields progress, and they progress because of citizen scientists who are able to do a lot of the work that professional astronomers can't. So that's mind blowing. So thank you for that, for clearing that up too.
Of course.
And we'll have time later to take everybody else's questions too. The fun part about being a moderator is I can just ask a question right away. But we'll be getting to the Q&A after everybody else has had their chance. So next up, we're going to have Steven Silverberg. Boy, I need a A little dry here
If I
today.
had a nickel for every time someone had gotten the name wrong in that exact way.
I assume they're trying to say Spielberg, right? And that's actually that's what my mind is doing, but not my mouth. I'm just having a hard time today. The weather here has been a little strange. But you're going to be talking to us about disk detectives, another field of science near and dear to my heart.
Indeed. So that should be sharing now. Cool. So hi, I am Steven Silverberg. I'm a postdoc at MIT, and I'm the principal investigator for the current version of diskdetective.org, where we work to find planetary systems with help from about 35,000 new colleagues, is how it's turned out. So sending my slides actually advance. There we go. So when we're looking for planets around other stars, it's interesting to consider, apart from planets, what things about our solar system can be signposts of there being a planetary system around another star. And if we try to take an alien's point of view of our solar system, and we look into the infrared, we see that the most notable thing is dust. We actually have lots of leftover dust from planet formation, collisions of planetesimals. If we look at this image of an estimate of what our solar system looks like, we see dust effectively from the Kuiper belt out past Neptune. And we see a nice little gap here carved out by Neptune. We see these around other stars as well. When we see it around other stars, we call them debris disks. And you can think of those as being kind of analogous to exoasteroid belts or exo-Kuiper belts. We find these in infrared data, so they show up in WISE, like was used in Backyard Worlds. Basically, you look for stars that have more infrared light around them than they should. WISE found a few billion sources. It's then a matter of finding the 20 to 30,000 debris disks and protoplanetary disks, the disks that have eventually formed planets, hiding in that very, very large haystack. So we created Disk Detective, and I'm going to switch what I'm sharing here right quick so that I can actually show you how the site works. So on the site, diskdetective.org, we'll show you images of the same target in wavelengths going from what our eyes can see through to mid-infrared, the wavelengths that night vision goggles work at. So we basically just look at all these images in succession and look for all the things that could make this a thing that, if you look just at their colors, look like a disk, would actually say that it's not really a disk. For instance, in this case, we can see that there's a few fainter stars in the background inside this red circle, which means that the light from those stars blends with the light from our star in the middle when we get out to the WISE wavelengths. So that would produce a false positive. We have extra light more than we expect, but that's due to the contributions from these other stars. And if you go further out, we've got a very, very, very bright thing over here that seems to be leaking in. So this isn't a good candidate. It's a bad candidate for what we're looking at in multiple different ways. So we can highlight that and move on. We can go through several of these, just serves more up as you go through them, which lets us go through to carve out, to narrow down the haystack from the things that, if you just went by their colors, could be disks, to the things that both have colors that look like disks, and if we look at their images, they don't look like galaxies or things bleeding through, etc. So, back. So on the site, you view things just the same way we did. You classify them, sorting them into the potential categories that an object could fit in, just like we did, and then hit submit. And if you find something particularly interesting about your object, you can classify it and then go on to Talk, which is our built-in kind of social media platform, and that will let you comment on what you saw, saying, yeah, no, this bleeds in, it's bad, or other things that are interesting about it. In particular, so Disk Detective first launched in January of 2014, and probably our most interesting discovery for me anyway, being someone who came to the project as a fan of M dwarfs or low mass stars, are these things that we've taken to calling Peter Pan disks. We discovered a star with what looked like a pretty substantial disk, the sort of disk that you'd expect to be around a protoplanetary disk, which those are usually about 5 to 10 million years old at the tops. We found one around a star that, best we can tell, is 45 million years old. You usually don't find things that are 5 to 10 times older than they should be, so we named them Peter Pan disks because, much like the Lost Boys in J.M. Barrie's Peter Pan, they seem to never grow up. We found one. There have been other discoveries in the literature. With the advent of new data from the European Space Agency's Gaia satellite, we've been able to find more. And we redesigned Disk Detective over the past year to try and find more of these. There are now 8 of them known. There's probably more to be found. It just took Disk Detective to actually be looking for them. So, as I said before, we've had contributions from 30,000 people. I wanted to highlight some specific contributions from people on what we call our advanced user team, the people who have gone well above and beyond. They started by accidentally classifying everything there was to classify on the site initially, and then they asked, okay, we've done that, what more can we do? So we've kept finding things for them to do, and they keep being, okay, what more can we do? For instance, Dr. Milton Bosch is a retired medical doctor who used to live in the neighborhood of NASA Goddard Space Flight Center, where this project started. He joined the project, fell in love with it, and one time when he was coming back to visit family, he asked if he could drop by. So we invited him in, and he got a nice tour of where James Webb was being assembled. And since then, he's come through a couple of times to Goddard and NASA headquarters to get a citizen scientist's perspective on what works best for citizen science. Hugo Durantini Luca is one of our biggest overachievers in that he discovered Disk Detective and fell in love with it enough that he introduced the project to the astronomy department at his local university in Argentina, brought them into our collaboration so that they were at least our source for Southern Hemisphere follow-up observations, and then took it upon himself to drive 12 hours across Argentina so he could go to the telescope and take follow-up with us. We've had several citizen scientists who are co-authors on articles about our work in journals. If you look at the author block here from one of the papers that I was a lead on, every name in this green block is someone who is one of our citizen scientists, the people who've gone above and beyond and helped us identify the objects we published in. And going back to Peter Pan disks, much as Atom and Backyard Worlds have incorporated their citizen scientists in press releases, we've done the same as well. Jonathan Holden, who I think I might have seen in the chat actually, put together this lovely image of an artist's rendition of what we thought the first Peter Pan disc might look like, and versions of it have shown up in science museums. There's a science museum in Michigan that asked to use this. So we've incorporated our citizen scientists all the way from classifying things on the website to writing the scientific articles about them to writing press releases telling the rest of the world about what all it is we do. So if you'd like to take part, we're definitely open for business. I uploaded about 2,500 new things to look at earlier this week. So you can go to scistarter.org/NASA. We're a partner with SciStarter. Hop there. You can start classifying. And if you've made 300 or more classifications, we invite you to consider applying to join our advanced user team because we want the contributions of dedicated citizen scientists like y'all. Thanks.
Thank you. That was so cool. Again, back in the day when I was a baby astronomer, I used to study these things, and we didn't know that much about them, and we barely had any images of them or anything. And now, to have these images, to be able to actually go through them and be able to find them like this is spectacular. And I'll note that Hugo and Jonathan apparently are in the chat. They're watching right now and they're getting quite a bit of love. So that's terrific. And I love the fact that you've incorporated citizen scientists to do things like artwork and all of that. That's fantastic. I love it. Okay, and let's go to our third panelist. And that would be Nora Eisner, who is the project scientist for Planet Hunters TESS. Just another fantastic observatory that is scanning the skies looking for planets around nearby stars. And so I will throw it to her. Go ahead.
Thank you for that introduction. Yeah, I'm Nora Eisner. I'm a PhD student at the University of Oxford, and I'm running Planet Hunters TESS. So today I'll talk to you about Planet Hunters TESS and how we can use Planet Hunters TESS to find planets outside of our own solar system, so these distant exoplanets. So very briefly, the field of exoplanets is just a really exciting and fast-moving field of astronomy. And astronomers, scientists, and citizen scientists all over the world are on a quest to find more of these distant worlds, and to answer questions such as, what kind of planets exist? Are there Earth-like planets? How common are these Earth-like planets? And are there planets like the ones we see in sci-fi films like Star Wars? So answering some of these questions will not only help us understand the universe and the Milky Way as a whole, but it will help us shed light on how the Earth formed and what will happen to the Earth in the future. So we want to find more of these exoplanets. So just very briefly, how do we do that? Well, one way to find exoplanets is using the transit method. So exoplanets orbit around their host stars, just like the Earth orbits around our very own sun. Now, if that exoplanet system is aligned such that the planet passes directly between us as the observer and that star, the planet will block out a smaller amount of light given off by that star. And you can see that in this little animation here. So if we measure the brightness of this star over time, and these measurements together are known as a light curve, we'll be able to see a small dip in brightness in those brightness measurements as that planet blocks out a small amount of light given off by that star. And that dip, that decrease in brightness, is known as a transit event. Now, in order to detect these transits, these kind of dips in the light curves, we have to continuously monitor the brightness of a really large number of stars. And that is what NASA's Transiting Exoplanet Survey Satellite, or the TESS mission, is doing and has been doing for the last 2.5 years. Now, the TESS mission provides us with hundreds of thousands of observations of stars, and it's our job to look for those tiny dips in the brightness that are caused by planets. And one way to find these dips is to use computer algorithms, but computer algorithms are very good at finding certain types of planets, but they tend to miss certain other types of planets. And in particular, they tend to miss longer period planets and planets around particularly variable stars and planets in systems where there is more than one star. But these planets, these more elusive planets, the ones that the algorithms tend to miss, can be found with visual vetting, or can often be found with visual vetting. And that's where citizen science and Planet Hunters TESS comes in. So let's talk a little bit about Planet Hunters TESS. Planet Hunters TESS is also online, and it's also hosted by the Zooniverse platforms, just like the other two projects that we just saw. So you can access it by going either to zooniverse.org or planethunters.org. And then you're shown a site that looks something like what we see on the screen now. So on the site, you'll be shown TESS data, and you're asked the question of, do you see a transit? And if you do see a transit, just like we have one here, so we can see that indicated by those dips, those decreases in brightness of this one star, you simply mark it on by drawing a box over those dips using your mouse. Now, I would absolutely love to show you a live presentation of Planet Hunters on the website, but the Planet Hunters TESS exoplaneteers are much, much faster at classifying the data than the TESS satellite is able to keep up and observe these stars. So unfortunately, we are currently out of data at the moment. But don't worry, more data will appear on the site in just a couple of weeks. But until then, we will look at some of the older TESS data to show you what the site looks like. So here we have an example of a TESS light curve, which I have labeled light curve A. And I'm going to show you 4 of these, and I will let you decide whether you think there is a transit signal in that light curve, or each of these 4 light curves, or not. And feel free to post your answers in the chat or in the comments, or to simply keep the response to yourself, and you can compare that to the answers, which we'll return back to in just a couple of minutes. So looking at this light curve A, do you see a transit? So I'll let you think about that one. Moving on to light curve B, this is of a variable star. So you can see this looks very different to the one we just saw. There are large changes in brightness. You have a zigzaggy pattern that could be caused due to star spots or stellar pulsations. And even though there is a lot going on in this light curve, we can ask ourselves the question of, do you see a transit? So moving on to light curve C, I would consider this a much better behaved star. You see that all that variability isn't there. It's nice and flat. And again, do we see a transit? And finally, we have light curve D, which is of a star that is yet again very, very different to the light curves that we've already seen, and it shows this very strange pattern. So as Stephen already mentioned, if you see on the Zooniverse project, if you see something strange, if you see something interesting, you can tell us more about it by clicking on that button at the bottom, the Done and Talk button, which will take you to a discussion forum for that specific target. And we'll come back to these discussion forums in just a moment. But first, let's see which ones out of those 4 light curves had transit signals within them. So here they all are again. Maybe I'll just give you just another couple of seconds to look at them and decide whether there is a signal in there. Maybe Phil can do a song or a little dance in the meantime. That was perfect. I will take that as a dance. All right, so the answer is that light curve C had a transit signal within there. It was quite a deep transit. Hopefully it was quite obvious. Hopefully you all managed or were able to see that. The one that was maybe less obvious was the one that was in light curve A. So there are 2 transits in there. They are very shallow. They are difficult to see. If you didn't see them, that is completely fine. They are very difficult to, even for someone like me who looks at a lot of these light curves, so that's not a problem at all. But if you do look at TESS light curves on Planet Hunters TESS and you do see a signal like the ones highlighted in yellow, you are encouraged to mark them on by drawing a box over them with your mouse. And you're also always invited to discuss possible planetary signals or even just really cool light curves that you come across, like the one in light curve D on the Planet Hunters TESS discussion forums. So these discussion forums are designed to let you flag any interesting signals and discuss your findings with either other citizen scientists or the Planet Hunters TESS science team. And here on the slide here, we just have some examples of some of the really great discussions that are going on. We have comments from Orion Lee, David Bundy, M. Houghton, 3 very active citizen scientists and all-around planet experts who, on these examples here, are carrying out additional analysis on transit-like signals. They're flagging potential planets and explaining the science responsible for some of these very strange signals that we see. So whether you want to join in by marking signals or by discussing them on the discussion forum, on Talk, you are helping us find real planets, and you're helping us find planets that the computer algorithms struggle to find. So to date, Planet Hunters TESS citizen scientists have helped to discover over 100 planet candidates, most of which have been published. And of course, because the citizen science part is the absolute backbone of this project, we invite the citizen scientists who help with the discoveries of these systems to become co-authors of any resulting publications, which you can see highlighted in red on these papers here. So very briefly, these papers include a sample paper that contains 90 planets that were found in the first 2 years of Planet Hunters TESS. We have a paper on a very long period planet orbiting around an evolved star. So this system is really exciting because it helps us shed light on what happens to planets as host stars get older. So this will also happen to the Earth or to the Sun. So it helps us understand what will happen to the Earth in the future. We also have a planet orbiting around 2 stars. So this was initially identified on the Planet Hunters TESS discussion forums. These types of planets are known as circumbinary planets. And finally, we have a very exciting new system that will be published in the next couple of weeks. So stay tuned to find out what that system is. Like I said, it will be out in just a couple of weeks. So these are just some of the examples of the types of systems that we have found with Planet Hunters TESS so far. And I definitely expect to find more in the future. So if you want to join the search for planets with Planet Hunters TESS, you can head to planethunters.org and start classifying data almost immediately. You're shown a very short tutorial video, and after that, you are ready to go and find planets. I also very briefly want to mention that we recently started holding live planet vetting sessions where you can join the Planet Hunters TESS science team, look through potential planet candidates, discuss signals, and decide whether a planet is real or not. So check out the Planet Hunters TESS discussion forums for more information of how to sign up to those. And last but absolutely not least, we will soon be launching the Planet Hunters Coffee Chat video series. So these will be a series of videos covering topics ranging from how to look at test data, how to analyze transit signals, and how to get started with some very basic coding. So those will also be launched very soon, so stay tuned for those. So yeah, I just want to end the talk by thanking the fantastic existing Planet Hunters TESS community of almost 30,000 citizen scientists who have completed around 17 million classifications over the past 2.5 years. And of course, also by inviting anyone who isn't already part of the project to join the search for new worlds. Thank you.
Wow, again, that's amazing. And I'm struggling with the numbers here. You've had 30,000 people classify 17 million observations. That's 500 on average. 500 a person? Did I do that math right? Did I drop a zero? That sounds about right. That's a lot. Wow.
We have some super users who classify absolutely everything. So we have 20,000 light curves a month on average given to us by the TESS mission, and we get through it very quickly.
It sounds that way. So if you're out there watching this and you want to be a part of Planet Hunters TESS, sign up and be ready, because apparently they get classified pretty quickly. That's phenomenal. I love this. It's hard to describe. I think I'm probably older than all three of you by a hair or two. Not that I know anything about hair, but it seems to me that when I was, let's see, the first planets were discovered in the early 1990s. So I was actually in graduate school at the time, and we didn't know if there were any other planets out there. And now we know of thousands, and we have people who are classifying millions of observations on this. And I've watched this over my career, over, I don't want to say my lifetime. Hopefully I've still got a little bit of time left in me. But to be able to see all this going on is phenomenal, and I just love that astronomers and software engineers and the public have gotten together to create these projects, to create them and to participate in them, such that we're doing real science here, and that just makes my heart soar. So I'm gonna throw this out to all three of you. Stephen mentioned these Peter Pan discs, but I'm wondering, what is the most astonishing, the weirdest, the most unusual thing that has popped up in these observations? And just go ahead and jump in, any one of you or all of you, because I'm very curious about that.
Yeah, go ahead.
Go ahead, Nora.
Sorry. I was going to say, in addition to all the planets, as I said before we started the session, there are a lot of really interesting star systems that come up, being these multi-systems where you have just multiple stars going around. There are no planets in these, but they're just also really, really interesting. So I find them fascinating, being a planet person and looking into the stellar community. Yeah, and one of them is this interesting triple system that we're really struggling to explain at the moment. But also a lot of really interesting planets, like the circumbinary planet and these evolved systems.
That's an excellent point. I mean, you've designed this to look for planets. That's not necessarily all you're going to find. There could be unusual objects out there that are floating around, and TESS is looking at the whole sky, so it's bound to find something interesting. And citizen scientists could find it. It's not necessarily a planet, still pretty cool. Adam, you wanted to add something?
Yeah, we've got so many interesting things, but the one thing, most surprising thing, I think, are what we're currently calling extreme subdwarfs. So we found some moving objects that were moving very fast that, based on their color, so how bright they are at different wavelengths, didn't really fit in with any currently known populations. And we got some spectra of these objects, and we're still like, huh? What is this? How do we explain this? So we have a theory. We think they're extremely old, extremely metal poor objects. So they really just don't have a lot of metals in their spectra, right? So they look very, very different than anything we've seen before at this cold end of the spectrum. You know, we've seen some metal poor stars, but these are extremely metal poor brown dwarfs. And so we had our first couple published last year. We've got a few more, and we've got some even more interesting stuff like that coming out really soon. So That's been the most surprising thing, where after we get a spectrum, we still are scratching our heads like, how do we explain this to the world? But that's one of the most exciting things, is the things you don't expect. So.
And I love hearing that, because we're looking at so many objects all over the sky. You don't always know what they are, and we're finding new stuff now that's not easily explained, and that's fantastic. And Stephen, you had something to add as well. Sounds like.
Yeah, a couple other interesting discoveries that from Disk Detective. We found what basically is a system analogous to Sirius, an A star with a white dwarf, so a much more evolved, more or less dead star next to it, that has a debris disk. So that's the first time anyone's found one of those. And we found a brown dwarf that appears to be about 3 million years old that has a disk around it. And this one's particularly unique in that it's very close by. It's only about 100 to 105 parsecs away. So we've seen younger brown dwarfs but further, that potentially have disks but further away. We've seen older ones close by, as Adams mentioned, but this one seems like it might hit the sweet spot of young and nearby and has disk that might make it a really useful target for understanding how brown dwarf systems evolve and whether or not brown dwarfs can have planets potentially.
Yeah, so Stephen just reminded me, there's been some really great cross-pollination between Backyard Worlds and Disk Detective, where we find things that are interesting to you and you find things that are very interesting to us. I'm pretty sure I got the spectrum for that object that you're talking about right now.
Almost certainly.
But we also have, and I think it was, again, a collaboration where we found a white dwarf with a disk that originally looked like a brown dwarf moving because it was moving in the infrared, but then it's there in the optical, and we're going, what is that? Help us, disk people. So, you know.
And it seems to be a white dwarf with a really, really big disk. And I'm trying to remember the direction the age timeline goes here. If I recall correctly, it's much older.
It's really old, like way too old to have
disks are. So we like finding things at weird ages over here at Disk Detective, apparently.
That's interesting. I wonder what would do that. And bit of trivia, the very first detection of a planet orbiting another star is actually from an observation that was taken in 1917. And it was a white dwarf that had an unusual spectrum, and they didn't know what to do with it. And it wasn't until a century later that we said, you know, that's a white dwarf that basically had planets and broke them up and is eating them slowly, and it's contaminating it. So you just never know. You find something unusual, and it could be the first of its kind. You just don't even know what it was. So I love everything about this. I love that you all are running these projects, and I love that we're ahead of schedule. So let's take a look at some questions. Oh my gosh, the Q&A is filled up, and I'm hoping that we may be able to get some from YouTube and Facebook, if those will get funneled to me. Caroline, if you can send those, and I can look at, let's see, some of the questions in the Q&A. Oh, this is a good one for Nora. Just to reaffirm this, when will you have new test data available for people to analyze?
Yeah, it's a really good question. I would also like to know. We wait for the data from the TESS mission. So they TESS observes around 20,000 2-minute cadence or short cadence data targets a month. And whenever that is processed by the pipeline, it gets given to us. It's usually at the start of the month. The dates vary a little bit. So unfortunately, I also don't know until the data is available. But I am expecting it to be in the first week of June, would be my guess. But I can't. We send out a newsletter when there is new data. So if you're signed up to the Planet Hunters newsletter, you will be sent a reminder.
Excellent. So a couple of weeks, and TESS is up there scanning the sky all the time. So there's always going to be new data as long as the observatory is running, right?
Yes, continuous data. So yeah, lots more things to be found.
That's really exciting. And I love that it's looking at mostly bright stars. So it's looking at relatively nearby planets. So those are the ones we're going to be exploring once we invent warp drive. So that's cool. Another good question here from anonymous attendee. What a coincidental name you have, anonymous attendee. What is the smallest planet you have found on Planet Hunter? And that's a really interesting question. There's a lot of science to that question.
Yeah. So we tend to be more sensitive to larger planets. The way the algorithms are much better at finding the small planets, because what the algorithms do is they have multiple of these transit events and they put them on top of one another to build up that signal. Therefore they're able to find these much smaller planets. Whereas with Planet Hunters, we mostly find single transiting planets. So we have less signal to kind of be working with. I think I want to say the smallest is around maybe 3 to 5, maybe 3 Earth radii. We're really more sensitive to the ones that are 3 and higher.
Okay, that's pretty good. Some dedicated, some other observatories have found planets smaller than the Earth, but it's pretty rare. Those are really hard to find. So there's a lot of science in observational science in that question, and so I thought that would be kind of fun. Here's a good one, Nicholas M., and I think this would be for Adam. How would we know if what we're seeing in one of those images is a planet or another object like an asteroid?
Oh, good question. So you won't, in the WISE images we inspect, you won't see many asteroids, if asteroids at all. The issue with asteroids is they're really close, and so they actually move too fast. So we take several WISE images and stack them together in what we call a coad, and they're faint and moving fast, and they just get completely blurred out. And because those happen on the timescale of days, where we're looking at things that move on the timescale of years, if that makes sense. So generally, if you find something moving, it's either way out in our solar system or beyond.
So let's assume it's not necessarily an asteroid, but it's a trans-Neptunian object, some giant ice ball out there. How do you know if it's something like something that's comet size, something small, versus something a lot bigger?
Yeah. So the tricky thing is there's kind of this things near us can glow. So we're looking at infrared light. So things kind of near us can glow in infrared from reflected sunlight. But once you get way out there, you don't really reflect sunlight as much, and so you won't glow in the infrared. We're looking for, something like Planet 9 should be big enough to glow with some of its own internal energy. And so we don't expect to see cold things in our data pop up. They have to have some of their own warmth, if that makes sense.
Yes. Well, it does to me.
Great question.
If someone has a follow-up question, I'm happy to take a look at that. And where did it go? Here it is from Hannah Redmond, and this would be for Stephen. How do you find brown dwarf planets?
I mean, you don't use disk detective for that. You use backyard worlds and Planet Hunters TESS to find the brown dwarf planets. But on the disk detective side, you can see whether or not a brown dwarf has a disk that could eventually evolve to form planets. So in our models of star formation, not quite brown dwarf formation, but star formation, we have a very big cloud of gas and dust that collapses down into a star with a disk around it. And then over time, the stuff in that disk starts to clump together and you get smaller things. And then those things clump together to make bigger things. And that's how you get planets. We see around this one object, this brown dwarf with a disk, it has the same sort of material as you'd expect for a protoplanetary disk just based on its thermal profile. Based on what we see, there's enough stuff there that it behaves kind of the way we'd expect a protoplanetary disk to behave, just scaled down to brown dwarf size. So eventually, in several million years, we would plausibly end up with planets around this one brown dwarf. But in the meantime, we can take further observations of this disk and use that to feed into our models of how these things might evolve. And that can give us more observational inputs for, can this happen? So we're using our observations to constrain our theories, which then gives us more things to get observations on to test, and a nice synergy of the theoretical and observational sides of astronomy.
As just a quick follow-up question that I have as well, you mentioned tens of thousands of disks potentially out there. How do you come up with a number like that?
So we started with, in Disk Detective 1.0, we started with an input catalog of 272,000 things to look at. That's 272,000 things where their colors in infrared, how bright they are at two different infrared wavelengths, hinted at them maybe being a disk. And then once we got through about half of that sample, we then said, okay, we have enough data here that we can start to do some statistics on what we expect. So we were able to look at our classification data from the website and say, okay, we looked at this many things and this fraction of them ended up being things that they might be disks, but we can't constrain if they're disks or not with our data. And that gets us down from 272,000 things to look at to about 21,000 things to look at, just based on people looking at these images and telling us, yeah, no, that is a star that has multiple stars next to it that will blend. Or, yeah, no, that definitely looks like a galaxy. Or that's really spread out and that might be a star embedded in the interstellar medium. So that number is really just from the statistics we have working through the classification data, because even the things that end up being not great objects for what we're looking for inform us more about how often we're going to find the things that we are looking for.
Excellent. Okay. And Adam, did you have something to add to the previous question? It looked like you did for a second. Maybe I'm wrong.
Maybe I did, but if I did, I have forgotten it.
Okay.
Thank you for asking.
Fair enough. There's a lot going on here. We have about 6 minutes left, and I'm looking through. There are a lot of similar questions. People sort of asking procedural questions like, how do I sign up? How do I get information about these? If I find something, and it's going to be written into a paper, how do I know? If you all have any general thoughts about that sort of thing, pipe up, chime in.
Yeah, I'll say a lot of those questions can be answered for Backyard Worlds if you just go to the frequently asked questions page. I think probably Planet Hunters TESS and Disk Detective have a similar thing. So feel free to explore the website a bit and see if we can't answer some of the questions there. I don't know how it works for other programs, but for us, anybody that has any part in discovering an object is immediately included as a co-author on the paper. If you contribute, we would like to make sure that you're recognized. So that's how we do it at Backyard Worlds.
Yeah, that's the same for us. I should add, so you can, on Zooniverse, I'm sure it's the same for your project, you can classify either by logging in or just without logging in. Unfortunately, if you don't log in, we don't have any of your details, so we can't contact you if you have help with a discovery. So the only caveat on your contribution, they're always counted regardless of whether you're logged in or not, but you do need to be logged in if you want to be included as a co-author.
Yeah, and I can't stress enough, being a co-author on a paper, it's very cool. And that's a pretty cool thing to put on your resume if you're looking for a job. And oh, by the way, found a planet around a nearby star. That's awesome. So yeah, there's so many cool questions going by. I like this one. Can the disk detector data pick up potential infrared anomalies that could be caused by life? That's from Mike Biddle in the audience.
The answer is potentially, but not in the way that you think. One of the things that we expect we might detect as a byproduct of our data are Kardashev Type 2 and Type 3 civilizations. This is going to be a very specific reference, but if anyone here has seen the episode of Star Trek The Next Generation where they randomly find Scotty stuck in a transporter buffer for 100 years, you'll recall that that episode involves what's called a Dyson sphere, which is an actual thing that's created where a civilization just built a shell around their star to capture all the star's energy. A Kardashev Type 2 is that. A Kardashev Type 3 is if you do that with every star in your galaxy. So in principle, those sorts of things might show up in our data as well as things with infrared excess. And we've actually been working a little bit with some of the folks at SETI to go through our classification data and see what things that aren't necessarily good disk candidates might be good signatures of Dyson spheres in our galaxy, or potential signatures of someone who Dyson sphered their galaxy?
I don't know if I want to know about aliens that advanced. If they can build a sphere around an object 120,000 light years across, that's terrifying. Okay, we have time for one more question. I was hoping, let's see, there's, for Nora, what's the longest period of a test planet candidate so far? And this is, I like this question for various reasons. Maybe I'll chime in once you're done.
Yeah, that is a very good question. So yeah, we do find the longer period ones. So the problem with the longer period ones is that we aren't too sure. We can't be 100% certain that what the period is, because we only have a single transit. So we have ones, so we estimate the period based on the transit duration, we model the transit. So we have ones where we estimate the period to be a couple of 100 days. But that is an estimate. The uncertainty on that is quite large. Also, I want to update my answer from before. I checked. We actually find planets down to about 2 Earth radii. So we have a couple of those. Yeah, so smaller planets with long periods of around up to a couple of 100 of years.
Yeah, I like that question because, I mean, it depends on the star. But how far you are from the star determines how hot your planet is, what temperature your planet is. It's easy to find ones close to the star because they transit so often, those transits stick out. But the longer period ones, as Nora mentions, those are harder to find. But that's a kind of, you have an Earth-like planet, an Earth-sized planet orbiting a sun-like star. Yeah, it's a year between transits. And so the farther out you are, the harder it is to find. But those are exactly the kind of planets that, we're really interested in. So I think that is all the time we have for questions. I will urge everybody in the audience again, if you're listening. If you're not listening, then it doesn't matter. So if you are listening, go to scistarter.org/NASA. You will see a huge list of all of these projects. It's a good way to keep all of them straight, or you can go directly to them as our panelists have talked about, our project scientists. This has been terrific. I've learned a bunch of things. I've actually written down notes for myself to follow up online. I'm going to do a lot of Googling, I think, this weekend. So I'd very much like to thank Nora Eisner, Adam Schneider, and Steven Silverberg for being here and promoting these terrific projects. And Caroline and Darlene Cavalier and everybody involved with SciStarter for asking me to moderate this panel. A couple of people have asked how they can contact me. I'm easy to find online, thebadastronomer@gmail.com. I write for Sci-Fi Wire. I write the Bad Astronomy blog. You can find me there. And again, thank you all. And I sincerely hope that everybody gets a chance to discover something out there, or at least participate in these projects and help out, because this is an amazing new direction that science is going, and it's extremely, extremely fruitful. So thank you very much.
Awesome stuff. Yes. And everyone, we'll see you in the next session. I'm going to go ahead and open up that room. That's Citizen Science Under the Sea, with a lot of great projects there. Then after that, we have CitSci-Sips with Derek Pitts, followed by a SciStarter happy hour. It's just a social hour. Grab a cocktail or a mocktail and come hang out with us. And then on Saturday, we have a whole host of sessions. It's a whole nother day. And you can find out all of that at scistarter.org/NASA. You can RSVP for all those sessions on Zoom, and you can also access all the recordings from today. So see you all under the sea. And thank you so much to everybody from today's panel.
Thank you.
Bye.